Find the equation of the tangent plane. We did this last class. Everyone, here's the surface. 2 times x minus 2 squared plus y minus 1 squared plus z minus 3 squared equals 10. And the point? At the point, 335. Can you find the equation of the tangent plane of this surface? Let me get my answer ready. X minus 3, y minus 3, z minus 5, all equal to 0. Well, what goes here, what goes here, and what goes here? The gradient factor at that point. The components of the gradient factor at that point. I'll do fx here, I'll do fy there, and I'll do fz here, and I'll plug in the points 3, 3, and 5. So what's fx to all that? And I'm talking about, like, think of it just equal to k. So we're just talking about the fx to this portion right here, so you can ignore that equals 10. Just to make sure it's equal to some constant, you're fine. So what's with respect to x there? 4, parentheses, x minus 2. I'll put that here. And what number do I got to plug in there? At the value x equal to what? Right? What's going here? What's that derivative? 2 times y minus 1 is a partial derivative at the value y equals 3. And then what are you going to do here? 2 times z minus 3 at what point? At the point z equal to 5. And you'll have the equation of a tangent plane. Isn't this cool? This is another way to get the equation of a tangent plane. What's this? That's a 4. Is that 4? That's 4. Okay, 4, 4, 4. That's it. There's the answer. There's the equation of the tangent plane. 4, 4, 4. There it is. These are the components of that gradient factor. Of this guy. You just found that's a 4, that's a 4, that's a 4, and you stuck it in front of there. Because that's what's going on when you come on a plane. Yeah, that's the vector that's perpendicular. It's a gradient vector, isn't that cool? Hey, they do have a part B to this. There's one like this on a practice set, so we might as well do this. It may be a while since you've heard this phrase, a normal line. And we've been always talking about tangent lines. What the heck's a normal line?
Perpendicular.
Okay, that'd be a line perpendicular at that point, tangent, right? So when they want you to get an equation of the normal line at this point. So it's been a while since we did lines. Remember lines? Mm-hmm. I'm going to put line x equals, I got to do 3 plus something t, y equals 3 plus something t, and z equals 5 plus something t. So what I need, these are the parametric equations of the line. Normal. They wrote line normal to the surface at the point. Well, to be normal to the surface, that means perpendicular to the surface. So right off some surface, I want to think of the surface like this. It's going to run in the same direction as the gradient factor. So guess what numbers I use right here? Use the gradient factor, right? Mm-hmm. If it's going to be normal to the surface, use the gradient factor, because that's how we do lines, right? Now, what is the gradient factor? Is that 4, 4, 4? Mm-hmm. There you go. I'll add that right there, and that would be the line normal to that surface right there at this point. The parametric equations of the line. I wrote the parametric equation of the line. You can write it in vector form if you want. I think on the practice set there, those practice problems, they are written in parametric form. So you'd be good. Hey, do you agree we could have done this if the surface was a sphere? What's the equation of a sphere look like? X squared plus y squared plus. See, what's cool about this now, this works great when you have z squareds in it. See? I don't know if you noticed this. In the last section, they always wrote z equal. They always wrote z equal to the equation. They always wrote that. So you can figure out that tangent plane. Nice. Got raised? Alright. Hey, the last thing we're doing today is section 14.7. Now this is on max values. Max and mins. And this is in section 14.7. 14.7, max and mins. And they give you some equation. How do you get max and mins in Calc 1?
Okay, double derivative, right?
And you all are great. You get the first derivative, right? And it was where the first derivative equaled 0 because the slope would be 0. But now we have functions of x and y, true?
Mm-hmm.
So what we're going to do to find max and min, step 1, is we're going to have to find the critical points. Just like you did in Calc 1. Find the critical points. And you go, what's that? Well, you told me it's where the slope equals 0, but now we have an fx and we have an fy. So when that's going to be the points where fx equals 0 and fy equals 0. So we're going to have to find that first. And then there's a second step. You'll love this. So once we get this, these will be the points where there's potentially a max or a min, right? But there's another kind of point. It's called a saddle point. Do you know what I mean by a saddle? Does anyone need me to put it like a saddle? Like, think of the saddle on the back of a horse. In one direction does what? This, and then the other direction can go like this. So that's what's going on with the saddle. So that's another point we can get from our critical points. Critical points may give us max values, min values, or saddle points. So to determine that, that'll be step 2. We calculate something called the determinant. Now the determinant is equal to this. And I'm going to draw a little matrix here. It's going to be the determinant of that matrix right there. I'll erase this part. We won't need this for section 14.7. We'll get this out of the way. The determinant is equal to, and I'll write it really big. This will be step 2 to 14.7. The determinant will be fxx. The determinant of this matrix. What is the determinant of this matrix? Where you go this times this minus this times this.
Mm-hmm.
So what does this math formula tell us?
fxx, fyy
times fyy
minus.
Isn't fxy equal to fyx by Clairaut's theorem?
Mm-hmm.
So I'm going to just write parentheses fxy close the parentheses squared. There you go. This will be step 2. Step 2 will be find your determinant. What was step 1? Step 1 was
On the critical points.
find the critical points. Find your critical points. That's step 1. Step 2, find the determinant. Okay, so this is just going to give us a number. Find the determinant at a point. Well, here's the scenarios. And if the determinant, we'll call it D. We're going to call this thing D, all right, everyone? This is D. If D is less than 0, you have a set point. So that's easy. If your determinant's less than 0, you got a saddle point. Yeah, but what if your determinant's greater than 0? If your determinant's greater than 0, go check the fxx. And if the fxx is greater than 0, do you all agree that's second derivative right there?
Mm-hmm.
Do you all remember about concavity? when second derivative was positive, like concave up, you know what it gives? It provides a minimum. See how I drew concave up? Concave up for second derivative greater than 0. So if the determinant's greater than 0 and f(x) is greater than 0, so I'll put and in here, then you have a local min. Will occur at that point. Let's do another one. And what if your determinant's greater than 0? And f(x) is less than 0. What's happening there?
Local max.
Someone drew concave down, second row is negative, concave down, it provides a local max. Or if you don't like the word local, you can think relative max. But let's leave this up. That's a summary of section 14.7. And this is how we'll find our maximums. Or we might find some, I put SP, what's this stand for? Saddle points. That's a saddle point. S-A-D-D-L-E points. Hey, there is one more if you want to add it. What if the determinant equals 0? If the determinant equals 0, then this test is inconclusive. Could be a max there, could be a min there. You'd want to investigate it some other way. Like use technology or something. Use Maple, make the graph, right? Look around that point. So if you do get some point where the determinant came out to be 0, I didn't want you to think, does that mean something? It means this test is inconclusive there. Cool? So if you want to add that to this, you can. If D equals 0, here, I'll put it right here. I got a little room. And if D equals 0, it's inconclusive, right? This whole test. We're going to explore that next in whatever that one's going on here some other way. So here's our first problem. Here's a function of x and y. How about x cubed minus 27x plus 3xy squared. The question is, can you find the critical points and find all local maximum and minimum values and saddle points for the function? So this is in 14.7. Find all local min, local max, and saddle points. This graph. You all know what I mean by a saddle point?
Determinant, right?
Yeah. So what's step 1?
You have to take the
Derivative.
derivative.
So let's find the critical points. Set fx equals 0 and set fy. Well, what's fx? Hardest part of the problem. What do you get for fx there?
3x squared
3x squared
minus 27
minus 27
plus 6y.
plus 6x
6xy, sorry.
plus 6y squared.
6y squared, yes.
Is that the derivative with respect to x?
No, 3
3y squared.
3y
Love it.
squared, sorry, yeah.
You're the best. Equals
0.
0. I'll put a big wall. Now don't forget, and what else we need to figure out?
Fy.
Which is 6xy equal to 0. Okay. But we got to solve this daggone system. This is the only hard part to section 14.7. Can you help me solve this system? And once we solve this system of equations, we'll have our critical points. And from there on, it's just going to be straightforward, just plug it into this little math formula to see whether you got local max or mins. But we're going to solve this system. So how do you solve the system equations? We go to one equation. There's 2 of them here, right? Pick the one that's easier. I think this one's easier. Do you agree? I pick the one that's easier. I solve for one variable. Then I plug it into the other one, right? And see what we get. So let me start out. And if 6xy equals 0, what would x have to be?
0.
So if 6xy equals 0, then you're telling me if x equals 0. So So when x equals 0 is one possibility, right? Now don't forget, we're going to get what's going on with x equals 0. Don't give up on the problem then. We also have to explore what was the other option. What else makes it 0?
Y.
So we'll come back to that, okay? But let's start with if x equals 0. So if x equals 0, we plug it over here. We're trying to find our critical points. I get 3 times 0 minus 27 plus 3y squared equals 0. Can you solve that?
Y equals plus or minus.
3.
Way to go! Not just 3, but
Plus or minus.
Yeah, plus or
y squared equals 9 and y equals plus or minus 3. So I'm going to get my list ready. Let's call them the CPs, the critical points, or the critical values, right? Looks like we got 2 already. X is 0, what is y? 3? What's the other one? X is 0 and y is?
-3.
Cool. The worst part is on the test, is it's like people just stop there. Like, all right, but we can't forget, we didn't explore what?
X.
The only tricky thing about a system of equations with 2 variables, I'm going to come back here and go, wait a minute, what else could it work?
If y is 0.
If y equals 0, this works. So we explored this. Now what if y equals 0? Maybe we can get more critical points. You never know how many critical points you're going to get. 2, 4, 6, 0, sometimes a 0. What if y equals 0?
Same thing, x equals to plus minus 3.
So 3x squared minus 27 plus 0 equals 0. I got you. Then x equals plus or minus or what? 3. So let's do it. Y is 0 and you get... Yeah?
Professor,
Cool.
that derivative of f of x is actually circle. If you look at it, you can do it that way also.
That derivative of the...
Yeah, because it forms a circle. 3x squared minus 27 plus 3y squared. And if you divide by 3, it becomes x squared minus 9. But in that way, you can also find it out also, you know?
Oh, right. Very good point. Factoring out of 3?
Yeah.
Yeah, because it's equal to 0.